not homogeneous. So,
very noisy too.
yeah. So we'll get this thing fixed, but I don't know when. So probably what will happen after 10 minutes, we'll turn it off. Okay. Okay, so let me start by saying that there are many things in Ricardo's lecture which I will go over more slowly when we do spinners. So I saw that there were many questions. The notation I will use is slightly different, I think slightly better than the notation he uses. But obviously, some of the questions you have might be answered not today, but tomorrow in the lecture I give about spinners. So up to now, I spoke about general things, but are there any questions about yesterday's lecture before I start today? So today is going to be very specific in the sense that I'm going to describe something which is real-world physics, which is a spin 1/2 particle in an electromagnetic background. And we'll see that the nicest description of it is using Lagrangian, which has supersymmetry. So it's not the usual thing people means when people mean supersymmetry. So it's it's one-dimensional, which is sometimes called supersymmetric quantum mechanics. So, go ahead, yes? If it's possible to what? I can repeat the question. You don't have to go up and down. So let me ask Thiago. I can't, but he can. Yeah. Você pode aumentar o volume? O ar-condicionado está fazendo barulho. Você pode aumentar o volume do microfone ou não? Tá bom. So we'll try, but probably the solution is what Gaston already did. So it's okay? Okay. So let me tell him not to. Não precisa. Eles desligaram o ar, não precisa. So the problem with raising the volume is then there starts being an echo and it becomes annoying. Okay, so supersymmetric quantum mechanics is sometimes called. So there are long reviews about supersymmetric quantum mechanics which don't discuss what I will discuss. So it's not going to be very useful. So this turns out to describe spin 1/2. And I am going to do it in an electromagnetic background. So these reviews do discuss spin 1/2, but not in electromagnetic background. So to start, I'm going to describe what is called a relativistic particle in electromagnetic background, which means spin 0. So it has charge, but it doesn't have spin. Okay? So suppose we have a particle with mass m and charge q. Okay. So there are, of course, many ways to describe it, but of course we know how its motion in an electromagnetic background. So essentially from the force law, so the force is something like F equals so I'm not being careful with, I will be careful later, but so something like Q, V, divided by C, something like that, right? So factors of C I'll probably get wrong just because I usually set C equal 1. Let me just find my notes. So I think it's actually correct. So this is, of course, you learn this non-relativistic, but it turns out to be also correct relativistically if the acceleration you think of is the derivative of the momentum with respect to t. So the momentum is not quite x dot. I mean, the momentum is remember, there's an extra factor of gamma, not Ricardo's gamma, but 1 over square root of. So if you use this definition of momentum, this turns out to be correct. Okay, so that's a relativistic particle with spin 0, means it doesn't, there's no spin which precesses. But as you know, if you have a particle with spin in an electromagnetic background, the spin will precess. Okay, so maybe, okay, I'll just write down the term. So the precession term is something like G times Q over 2mc. So you can understand this term is coming from, this is the work done on the particle. So the S is the direction of the spin. And depending on the direction of the B, it has different energies. And this tells you that there's a force if it's changing the energy. Okay? And this is just the divergence. Okay? And as I said, the spin precesses. So you have an equation like this. G E. So I hope people can read it. So these are the equations of motion for the spin. So dot is x dot is always going to be dx dt. Okay, so these equations are, of course, well known. And the question is, how do you get this from a Hamiltonian Lagrangian description of the particle? Okay? So I'm going to use Lagrangian description. And it's well known how to get without spin. But with spin, it's not so well known. And in fact, the Lagrangian that works, this G is gyromagnetic ratio. It's just some constant, which has this fancy name. And it turns out that the Lagrangian that I'm going to tell you only works when G equals 2, which happens to be very close to the value of G if you have an electron. So, so G is actually a parameter that you can choose. Let me have to. That you can choose as you like, but of course, electromagnetism has its specific G, and it turns out for an electron it's G, 2 plus quantum correction. So it will turn out that the Lagrangian that describes this theory has a supersymmetry. It's supersymmetry in one dimension. But only when G equals 2. Sorry, this should be Q. Okay, any questions up to now? So what I'm going to give you first is Lagrangian that describes just this part, okay? So spin 0, which some of you may have seen before. It's in many textbooks, Landau Lifshitz, or any textbook that does relativistic particle and electromagnetic background has it. So the starting point is just the Lagrangian for, so this is the action. I'll use curly S for action. So again, the dot always means dd, well, probably means dd tau here. But I won't be too specific what I mean by tau or t, but here I mean dd tau, so maybe I should. So what I'm using now is a 4-component notation, so I should have written it out more explicitly. So some of you may have seen this action when you discuss special relativity for a particle of mass m. Okay? So you can think of this as being the integrand as measuring the distance between two different points. And minimizing the action minimizes essentially the geodesic that separates the initial and final point. Okay? And this is relativistic. So this is A to Mn. It's the Minkowski metric. Okay? So of course, if you go to the non-relativistic case, this is going to give me something like a constant plus just the kinetic energy. It'll give you something like 1/2 m v squared. So this is just a 3 vector. So non-relative plus relativistic corrections. It turns out this action here has a gauge symmetry in the same sense as the gauge symmetry that Ricardo will be talking about, which is you can parameterize this tau as you like, because this is, remember, is dx d tau. So if you change tau to some other coordinate that you're using to parameterize the line, the change in d to d tau in the denominator will change the d tau here. So d tau will go to d tau prime. D tau. So if you change coordinates from tau to tau prime, this is, of course, equal to this. And, of course, dx d tau will go to dx d tau prime times d tau prime d tau. And because this has 2 factors with the square root, this cancels this. So it turns out this is equal to d tau prime, x dot prime, x dot. So I'm not going to go into this, but the point is that the action has this local symmetry, which sometimes is called reparameterization symmetry. So this object here is really a length, so it's a physical. It doesn't depend on how you parameterize the length. Okay? Okay, you can, of course, compute the equation of motion. So the equation of motion is just the usual equations you get for Lagrangian systems. So you have d d tau so this implies, of course, it only depends on x dot. It doesn't depend on x right now. But now I'm going to make it a little more interesting. I'm going to couple it to an electromagnetic background. So that introduces a new term, which is proportional to the charge times this field that is the field for the photon, or if you like, it's the potential. So, of course, FMN so FMN describes the electric and the magnetic. So you can think of this as a 4x4 matrix. It turns out to be anti-symmetric, obviously, because if you switch M and N, there's a minus sign. So normally one uses the convention is EX, EY, EZ. It's anti-symmetric, so these are 0. And here you get, I guess, BZ, BY, BX, and here would be minus BZ. So this contains all the information about the electromagnetic background. Okay? AM is a function of x, so it can depend on the position in space-time. And now, in order to write the Lagrangian, this index here on the potential contracts with this index on it. Okay? So now when I compute the equations of motion, you get a contribution from dl dx dot, from, of course, from here and from this thing. Sorry, this is dx. But you also get a contribution from here coming from the derivative of AM with respect to x. Okay? So this implies the equation of motion, straightforward to compute. You get Cm, you get a factor of half from the square roots, but then there's the 2 of them, so you get the Cx x dot m. Let me put an m here just to make it more explicit. Divided by square root. So dd tau of this. And you get also a contribution from here. So I guess I should have put that. So that comes from this term here. But then you get an additional term coming from the derivative of am with respect to x. So this is equal to q d dxm. I'm going to change, just to not repeat the indices, I'll change this to an n. Okay? Let me write this as x dot n. Just notation. Okay, any questions about how to get to here? Okay, so this is just standard equations of motion for a Lagrangian. Okay. Now you see, I'm going to expand this dd tau here, because dd tau, of course, although am has no explicit dependence on tau, it gets dependence because x depends on tau. So this equation actually implies that dd tau of cm x dot, and by square root of x dot m, So if I make a mistake on the blackboard, please correct. Is equal to, I'm going to write this term as q times x dot n. So that's from this term. But then I'm going to use the dd tau of this am of x is equal to dxn, just using the usual chain rule. Okay? And because this is on the other side, I'm going to just turn it to this side. And now you see this is equal to dxn an. So the equation of motion you get from varying this action here implies this equation of motion, and this is, of course, equal to q x dot n fmn. I should put my indices. Okay, any questions? Yeah. This one? Okay, very good. Thank you. So let me put all the indices down here. Now you're happier? Okay. Any other questions? Okay. So this equation here turns out to be precisely this equation here. So to see that, we have to write down what x dot is. So remember x0, x1, x2, x3. You can think of it as t, x, y, z. I guess there's a c here. Right? So sorry, I use x twice, but I think it's clear what I mean by x. And then you expand this in terms of E and B, and you see when n is 0, then this just gives q times essentially just 1. And when this is 0, when one of these is 0, it just gives you the electric field, right? So what if I write the, so let's look at the terms here in which m goes from 1 to 3. So that's going to be a 3-component vector. So that's going to be m acceleration is equal q. In this case, it's going to be q times e. That's just from the when the m is in the vector direction, when it's in 1, 2, or 3, and n is equal to 0. But then there's another contribution if m is in the vector direction and n is also in the vector direction. So that's going to give you a B field, right? That comes from here. So when this is in the vector direction, or in the spatial direction, that just gives you the term q. I'll get the factors of c right in a second. So There's probably a factor of C that I left out. So as I said, I get that wrong. Okay, so x dot 0 is actually not 1, it's C, right? Because x0 is equal to CT. So there actually should have been a C here, and no 1 over C here, which means I have a C here, so that's this C here. Okay, so now I got the factors of C right. Okay, so this gives me the equation of motion I want when there's no spin. Okay, so if you haven't seen this before, you might want to look at some references. So Landau and Lifshitz does this classical field theory book, but I think any book that discusses relativistic particle and electromagnetic background, you'll see this. Okay? So it's a very nice way, so just to summarize, the equation of motion is just ma equals q x dot n fmn. So in some sense, that's convincing, right? Electromagnetism is somehow as simple as it can be. Now we want to generalize this to the case when we have spin. Okay. Any questions? Okay, now what I'm going to tell you here is the easiest way to do it. There are much more complicated ways to do it, which don't involve fermions, don't involve supersymmetry, but they're a mess. I guarantee you they're a mess. The easiest way to do it is to introduce fermions. So of course, everything here is bosons, right? X is boson. Of course, electromagnetic background is boson. I'm not going to fix that. But I'm going to now introduce some fermionic variables in addition to these X's. So I think I'm going to erase this. So what are the variables I'm going to introduce? Instead of just having xm, which depends on tau, I'm going to introduce a variable psi-m, which also depends on tau. This is fermionic in the sense that I defined for you yesterday. It's not a spinner, but it's fermionic. Okay, so classically, it satisfies the usual that it anti-commutes with itself. When I quantize, it will turn out to satisfy some anti-commutation relation similar to the commutation relation of x, right? So normally you define x and p to satisfy some kind of commutation relation of this type. And psi m with psi n, so classically they will anti-commute, but quantum mechanically, they're going to satisfy a relation of something like this. Okay. So how do we do that? So let's just write down so if you write down the action Cm, let me write down this action first. So if you start with this action and you canonically quantize, you essentially define the momentum with respect to this action as defined as the derivative of the Lagrangian with respect to x dot. That's the usual way you define canonical momentum. Okay? So that means x dot and x are not going to commute. Okay? And p is, of course, equal to mx dot. Normally one puts a factor of 2 there. I'll put a factor of 2. What do we want to do in order to get this kind of anti-commutation relation? We're going to add a term here, which is going to be psi dot m, psi m. And I'm going to put the factor of I for a region which will become clear in a second. So this only has one derivative, not two derivatives. So if you try to find some other kind of p, let me call it curly p, to be of this type, then you see with this type of action is just going to be something like I times psi m. right? Because if I take the derivative of this Lagrangian with respect to psi dot, it just pulls down this term and I get psi. That means the canonical momentum to psi is psi itself. So that's why you get this kind of anti-commutation relation. So that's something typical which you also see in Ricardo's lectures, that when you have bosonic degrees of freedom, there usually are derivatives on each of the bosons. Whereas if you have fermions, usually there's only one derivative. Okay? So the Dirac equation only has a single derivative, not two derivatives. Okay? Now, of course, if these were bosonic, this would be a total derivative, because obviously, if I just have a single derivative on the x, if I consider that x dot mxm, that's the time derivative of x squared. So that would just drop out. So it's important that these are anti-commutating, because then this is not dd tau of anything. Okay? Now, the reason why you put an I is because you want this to be Hermitian. So if you take the Hermitian product, if you take the Hermitian conjugate of I psi dot m psi m, you have to exchange the order. So this is equal to minus I psi m dot. Or obviously I goes to minus I, but I exchange the order because it's Hermitian conjugate. And now you see you get an extra minus sign by switching the order again. So that's why you put the I here, to make it Hermitian. Okay. So you'll see this I also if Ricardo writes down Lagrangians for fermions. Okay, any questions? Yes? Sorry, a question here and then go ahead. The psi is what? The psi is Hermitian, yes. Question?
Yes. What exactly is the x? Because we're dealing with quantum mechanics. So
Yeah.
have
X is the position of the particle at a certain position on the world line. So I should have said this. I should have drawn a picture. So here's tau. It's the world line of the particle. This is the direction tau. And xm of tau is just the position of the particle in space and time at tau equals whatever. Okay?
But in quantum mechanics, that was my question. In quantum mechanics, we don't have that number well defined.
So in order to quantize, you actually have to gauge fix this. So I'm going to say a little bit about that before. This action, as I said, has a reparameterization symmetry. And when you have a gauge symmetry, in order to quantize, you have to gauge fix. So this is something you'll see again in field theory if Ricardo talks about this. So gauge fixing, you can gauge fix, for example, to set tau equal to the usual time. That's one gauge fixing. So after gauge fixing, then you can quantize, and then you will find, for example, these relations that I discuss here. Was that your question, or?
More or less, that was indirect. But the question really was why we can define the x dot when generally that's the x dot is not a number but a function. Quantum mechanics.
So you can work in position space or momentum space. In position space, as you state correctly, you can't simultaneously define x and x dot. But classically, of course, x and x dot are just numbers. They're just ordinary functions. So the fact that they don't commute means that you can't simultaneously define x and x dot. I don't know if that's what you're asking.
Now listen, so you are working with momentum space.
For example, if I work in momentum space, x dot is well defined, and x is some operator like d dx dot, or vice versa. Okay, so psi dot and psi, so normally if it was classically, as I told you yesterday, fermions anti-commute, okay? Classically, x and p commute, right? But quantization tells you that you can't simultaneously identify x and p, right? Because they don't, the usual uncertainty relation. There's a similar uncertainty relation for psi's. So quantum mechanically, they don't anti-commute. That's right. Other questions? Yes? I'll get there. That's a good question. Thank you. So, thank you. Any other? Okay. Good. Let me go to your question now, which is something I was going to say. So, this action is reparameterization invariant. What I will tell you in a few minutes is that this action has a global symmetry. So of course it's invariant under translations, because obviously if I shift x by a constant, nothing changes. It's invariant under Lorentz rotations. Okay, that's obvious. It has another kind of symmetry, which is a symmetry that relates x with psi. So the symmetry is, so I'll call it Q. So remember P, sorry, I call too many things P, but the supersymmetry algebra that we saw yesterday is, we had a symmetry algebra like this, right? And many people ask me, well, what is, so P, everybody knows what that means, but what is Q? Okay, so it's a generator which transforms the variables or the field in some way. Okay, so here I'm going to tell you exactly how Q transforms the variable. It's going to take Qm is equal to psi m. I think I got it right. Sorry. And Q of psi m is going to be equal to x dot m. Whereas P in this case, and I'll call it, not to be confused with this P. So this is something that, okay, it's already confusing. These letters here, so let me, I'm sorry for changing. This capital M is just 0. Okay, it only takes one value. Okay, just remember, I have in this lecture, not like the last lecture, I'm using small m to describe the space-time. Okay. I'm using capital M for this supersymmetry algebra. Remember, this d equals 1, so this is m, capital M. Which means m is essentially just in the tau direction. There's no other directions. So how does this P act? It just takes xm into, let me call it I x dot m, and P of psi is equal to I psi dot m. I think I put the I, I just want to make sure, yeah. So this curly P, or capital P, is like I dd tau. So it acts like a translation in the tau direction. Okay, just so I have, of course, the usual Poincare symmetries of the space-time, but this d equals 1 is actually the one-dimensional, just translations in tau. Okay. So it's not difficult to show that this Lagrangian is invariant under not just this symmetry. So this is obviously just tau goes to, no, sorry. Under this symmetry here, the Lagrangian, so P of the Lagrangian is of course dd tau of the Lagrangian, right? So it doesn't leave the Lagrangian invariant, but it shifts it, just takes it into dd tau. And because we're ignoring surface terms, it leaves the action invariant. So this takes S which is a total derivative. Okay. So a constant shift in tau doesn't change the action. Okay, it shifts the Lagrangian by the total derivative. Similarly, this transformation here will not change the action. Okay, so let's see how it works. So the Lagrangian is m over 2 times x dot m plus I. So if we take q on the Lagrangian, it just acts on each of these terms. So it gives me m over 2. It's an infinitesimal transformation, so it will give you something like I times psi dot m acting on the first term. Give me another factor acting on the second term. And then you get a contribution from here, which is going to be plus I. I hope I didn't make a mistake. X dot m psi m. And then finally you get plus I. And I think I'm going to make a mistake here. Here you have to be a little bit careful because Q is fermionic. So when you pull it to the psi dot, it gives you an extra minus sign. So it's going to be minus I x dot m. So this is Q on the Lagrangian. And this should be equal to, if I didn't make a mistake, should be equal to total derivative. So it should be equal to m over 2 times dd tau of probably 2I. Let's see if I can get it right. So it should be I made some mistakes. So this is psi dot, right? So let's do it more carefully. This is I. So from the change in x dot, I get plus I psi dot from the first. I get another one from the second. That's from this change. Then I get the plus I x dot. Sorry, psi goes to x dot, so psi dot goes to x double dot. That's what I was missing. Okay. Now it should be right. So it should give me m over 2 I x dot m psi m. Now I think it works. This term is going to cancel one of these, and then you just get a total derivative. Yes? Okay. So P is an operator which just shifts tau to tau plus a constant. So it takes x, let me just finish. So it takes x of tau into xm of tau plus a constant. So let's do it, let's say the constant is epsilon. So this is going to be equal to xm of tau plus epsilon x dot m of tau. So if you like P, you can think of as P. P is the infinitesimal version. So P is equal to xm of tau plus epsilon minus xm of tau. So that means P of xm of tau is just equal to x dot m of tau. I guess with a factor of I. So probably the way to do it correctly is something like this. Well, I think it depends on your definition of epsilon. So this is what I mean by, this is what I meant by P acting on X. Similarly, P acting on psi does the same thing. So P acting on any function of X and psi will just take the object into its derivative with respect to tau. So that's what I said here. So this is the change in S. So S, the action will go to the same action plus a total derivative. So if you like P of S is equal 0, right? Because it takes the action into the action. So P leaves the action invariant. It doesn't leave the Lagrangian invariant. It shifts the Lagrangian by the total derivative. Yes? Okay, good question. So Q is fermionic. It's a fermionic operator. So normally, if you have bosonic operators, you don't care about the order that it acts on the variables. But remember, fermionic variables classically anti-commute. So when I pull so this Q has to act both on this psi and then on this psi. When it acts on this one, it just changes into x dot. But in order to act on this one, I have to pull it through this one. When I pull it through this one, it changes this plus I to a minus I. That's why you get the minus sign here. Yes? So that's an assumption. You could have asked the same question about P. So I guess, I don't know the right word in quantum mechanics. Linear operators act in this way. So all symmetries that we discuss in quantum mechanics act in this way. They always act by chain rule and I don't know what the right mathematical word is, distribution, or there's some word for it that I don't know the answer to. Any other questions? Okay, so this is essentially very simple. So you might say, okay, who cares? So I have a Lagrangian which has this property. It satisfies these anti-commutation relations. What does it have to do with spin 1/2, for example? Okay, so so maybe before I say what it has to do with spin 1/2, let me say why it's called supersymmetry. So supersymmetry was this rule here, right? So if there's just one direction, the supersymmetry algebra is very simple. It's just q squared is equal to, let's get the signs right. I think it's just p. Q squared equals p. Yes? We can show that it commutes. We don't have to assume. So these are the rules. And now we can compute the algebra. Okay? So let's take q squared. So we know what q of x is. So we just do it twice. So this is equal to q of I psi m, which is just equal to I of x dot m, right, using those rules. And we can take q of psi m, which is just q of, so q of psi m with these rules is just x dot m. We take q of that and we just get I psi dot m. And we see this is of course equal to p of xm, and this is equal to p of psi m. So we check that q squared equals p. We could check that q commutes with p. Let's do it. I didn't think of doing it, but let's do it. So qp on xm is equal to q of pxm. P of xm is just I x dot m. Then we take q on that using the rules here. We get minus psi dot m. Right? So you get two factors of I, so it's minus psi dot m. We could have done in the opposite order, p of q of xm. So first we get p, q of xm is I psi m. And then we take p of that, and that just gives me minus, again, psi dot m. So that means qp acting on something is equal to pq, so they commute. So qp. Okay, any comments, questions? So we have supersymmetry algebra, okay? But still, it looks kind of silly, okay? So what? Okay, let's see why this is called spin 1/2. So, of course, we know what Lorentz generators are. So when you have a Lagrangian with invariance under Lorentz rotations, you can always define a conserved current, right? So this is another current, how do you want to define it? And it just comes from constructing the, if you know the Lagrangian, essentially, it's something like, dl with respect to dxm times delta xn, it's something like this. Then you obviously have to do the same thing for the fermions. And I think that's enough. So this is delta psi. So this is just a well-known method for constructing the angular momentum tensor, okay? Where delta xn is just a transformation of x under Lorentz rotation, and delta psi n is the transformation of psi under Lorentz rotation. So in this case, if you just plug this in here, you find that this is equal to x dot m xn minus x dot n xm up to factors of 2, probably. It's probably something like this. Probably there's an m here also. And you get a similar contribution from the psi's. It's just because delta L delta psi dot is just psi. And the transformation of psi under a Lorentz rotation, it just rotates the n index in the usual way. Remember, this is not a spinner. Don't confuse this with spinners. Okay? It's a fermion, but not a spinner. Okay, so this part is what everybody calls the orbital angular momentum. Whatever's left over, people call spin. Okay, so the angular momentum generator is always equal to orbital angular momentum plus spin. So we're going to divide this as the spin. So it looks kind of crazy because psi's are fermions, and spin, of course, is some number, right? Spin 1/2, spin 1, spin 2, etc. Okay, but we want to go further, so we want to see why this should be identified with spin. So we're going to, now there's something I'm going to tell you here which I'll try to explain later, but not in great detail. When you go to the non-relativistic case, psi 0 equals 0. Okay, I'll explain this later to you, but non-relativistic implies psi 0 equals 0. When psi 0 equals 0, this tensor only has 3 independent components. Because remember, it's antisymmetric in M and N. So this I'm going to call SMN. And you see SMN vanishes if M equals 0, because in that case, one of these psi's is going to be 0. So probably there's a half here. So this is equal to M over 2. One thing I didn't say is these two terms, of course, are the same because the psi is anti-commute. Okay, remember, this n is different from this m. So classically, quantum mechanically, this is just equal to m. So this is going to be my definition of SMN. And I forgot a factor of I. Sorry about that. There's an I here coming from this I here. So again, if I make a mistake or you see something that doesn't look right, just say it. Okay? So there's an I here. So as I said, in this non-relativistic limit, this only has 3 independent components, which you can think of as S12, S13, and S23. Okay? So I can think of this as being epsilon JKL, SKL, or if you like, it's just IM psi 2, psi 3, psi 3, psi 1, psi 1, psi 2. So this I'm going to identify with the spin. Again, it looks funny because the psi's are fermionic, so how can this be a spin? Any questions? Yes? Good. Okay, so I should never erase something and then put it back. But so this was equal to plus I psi n minus psi n, right? If I change the order of these, I get a minus sign. So this is equal to 2 times psi m psi n, right? So the 2 cancels that too, so that's where this comes. Okay, any other questions or comments? There's just this term. Okay, sorry. In the definition of delta psi n, it depends on, you could have asked the same question here, right? How did you get 2 terms? Probably I should have both terms. Probably I should have written this twice. So this thing minus delta L, I'm sorry. So I'm going to use this notation, which I introduced yesterday. Okay, that's my mistake. Thank you. Any other questions, comments?
You have that part of spin is, at least the one that you wrote up there, is the commutator of MN.
The commutator, but it's the same as twice this because they anti-commute. That's what I answered before. This is equal to this, factor of 2. Okay, any other questions? Okay, so let's see how to get the number out. So to get the number out,
Sorry,
Yep.
different question.
Go ahead.
So we can know both numbers simultaneously because of the uncertainty relation. Once that would be equal to the spin, and the spin is something generally.
I don't know if that was a question or a comment, but let me tell you how to get the number out of spin, okay? So let's compute s squared. So this is obviously going to be equal to Im psi 2, psi 3, psi 2, psi 3, plus psi 3, psi 1, psi 3, psi 1, plus psi 1, psi 2, psi 1, psi 2. Sorry, times this should be squared, minus m squared. Right? So minus m squared just because of the Im squared. Now you might think this is 0 because psi 2 squared is the square of a fermionic object, so this is equal to, if I switch the order, I get the minus sign, so that's going to cancel this. So I'll get psi 2 squared, psi 3 squared, plus psi 3 squared, psi 1 squared, plus psi 1 squared, psi 2 squared. Right? All I did was switch the order, and that gives me a minus sign, which cancels this minus. But now, remember, quantum mechanically, psi 2 squared is not 0. So we saw that here. I hope I didn't miss factors of 2. Yeah, there's a mistake here. This should be over m. So the m here is essentially because, as was pointed out, there's an m here, so there's an m here. So if I do psi with psi, it doesn't give me IH bar. It gives me IH bar over m. And in fact, there's an extra factor of 2. No, this is what I have in my notes, so I think this is right. And there's a minus sign. So because of this I, there's a minus here. Okay? Sorry. Okay, so now we can use this equation. So that tells me that psi 1 squared, which is, of course, half of this if m in, this is equal to minus h bar over 2m, right? Which is equal to psi 2 squared, which is equal to psi 3 squared. So all of these are equal to minus h bar over 2m. So you plug that in here, and you get m squared. You get the 1 over, right? Here you get h bar over 2m squared times 3. Right? The m squared cancels the 1 over m squared, so you end up getting 3/4 h bar squared. So you find that although S is some object constructed from these fermionic variables, because of this anti-commutation relation, you find that S squared is just an ordinary number, which is equal to 3/4 h bar squared. And now if you remember from quantum mechanics, this is equal to S times S plus 1 times h bar squared, where S is the spin. So we see when S is equal to 1/2, we reproduce this 3/4 that we wanted. Okay. So we showed that this description describes, if we interpret psi, this is the spin, we find that it describes a particle of spin 1/2. Yes? Yep, that's correct. That's why there's an h bar in spin. If h bar is 0, then spin, everything is spin 0. Yeah, just an ordinary rotation. Any other questions? Okay, so now life is a little more interesting. You have this Lagrangian which has supersymmetry, and I convinced you, I hope, that it describes a particle of mass m, charge q, and spin 1/2. Actually, I didn't do charge yet. Okay. Now the last part, which is I think the thing that clinches that this is actually useful, is you add the interaction with the electromagnetic background. So remember, for the particle of spin 0, we added a term here, which was q times am of x times x dot m. Now, this term you still want to keep, because remember, it's that term which generated this term in the acceleration. But we want an additional term, which is going to generate this. The additional term we're going to add is equal to fmn x times psi m psi n. And now this is a factor of I over 2. So this is an additional term, which is going to change the equations of motion to include these terms here, where g is equal to 2. Okay, so I'll put g equals 2. So let's just see how that works. So now when we compute the equations of motion, we'll of course get additional contributions. So let's just do quickly the equation of motion for x. So there's something I'm going to talk about in the very end. I don't want to mention it now, but remember, before there was a square root in the action. I'm sorry? Yeah, okay. Give me 2-3 minutes. Okay. Okay, so I'll say it now, okay, so I don't have to repeat it. Before there was an action which had a square root in it, and the action was reparameterization invariant. Okay? This action does not have a square root in it. It turns out to be, this action, there is a way to write this action with reparameterization invariance. It's more complicated. The action with reparameterization invariance also has a local supersymmetry. So You can think of this as being a global symmetry, this P and Q, but it turns out the local action has a local supersymmetry, in addition to the local reparameterization invariance. If you gauge fix both the reparameterization and the local supersymmetry, you get this action here. So after gauge fixing, you just get the global supersymmetry and you get translation symmetry. So there's a version of the action with spin 0 in which you don't have the square root also. You just drop these terms. If you go ahead and compute the equations of motion, for this you get the right equations of motion, but it's in a certain gauge, okay, that I don't want to discuss. It turns out that in the gauge which I discussed, in which you start with the more general reparameterization invariant action, this constraint here comes from the gauge fixing. Okay? Actually, the Lorentz invariant way of writing this constraint is x dot m psi m equals 0. So when you're working in the non-relativistic case, x dot 0 is much bigger than the others. X dot 0 is essentially equal to c, and the other, in the spatial directions, it's equal to v. Okay, so when v is much less than c, this implies psi 0 equals 0, non-relativistic. So that's just a side comment. Okay, so let me just finish by, and actually this will be part of an exercise. So let me finish by telling you that the equations of motion you get, so let's just find the equation of motion for x. And as an exercise, I'll ask you to derive this equation of motion for s. So s is, of course, defined here. And so when you take the time derivative with respect to psi, you'll get a contribution from here as before, but you'll also get a contribution from here. Okay? And this contribution here is going to give you the precession of psi. So let's just do the x one just to see how that works. So dl dx dot dd tau is equal to dl dx. And of course, the equation of motion for psi, I'll write it down so just so you know what it is. It's kind of obvious. It's dl d psi m is equal to dl d psi. So these are the two equations. Let's just see how this is modified in the case of adding this term. Okay. I guess I can do it here. So of course, the contribution from here we already considered. So that we already computed. We had MA was equal to, probably I erased it already, it's something like Q times X dot M. Let me write it. So up to sines, it was something like this, right? That came from this term here. Okay, so we already did that part. The other contribution, of course, comes from here. Right? There's one other contribution because dl dx, fm and x depends on x. So we get an additional contribution, which is, I guess, I over 2 d dxp. So let me call this p instead of fmn psi m psi n. Right? It just comes because fmn depends on x. So when I take this derivative here, I get this extra contribution. Now psi m psi n, at least in the non-relativistic case, we already identified with s, right? I erased it already, but s was something like, I forgot the factors, but it's something like psi j, psi k, epsilon jkl. So you had an equation like this. And we see this has precisely the form here. So when psi 0 equals 0, that's the only thing that contributes here. So this term here becomes just, so let's just So this term here is equal to IQ over 2. D dxp, that's just the divergence, right? Of, so fjk sjk, right? So remember, we're assuming that psi 0 equals 0, so you just get the j goes from 1 to 3. And when j goes from 1 to 3, the electromagnetic intensity is just B, so this is just equal to IQ over 2. There's a factor of m because actually S is IM, so there's a factor of m here. So if I do things correctly, it's probably something like B dot S. Okay, and that's, okay. Of course, two factors here. There's a factor of C I lost somewhere, and there's a factor of I okay, there's an I here, so that cancels this I here. So. Okay, so obviously there might be some sign errors, but this is the idea. By adding this term here, you reproduce the desired correction coming from the contraction of the B field with a spin. Okay. And then as an exercise, you can work out this one. And one final exercise is show that this term here is invariant under this transformation. So I wrote this down, but I didn't show it was supersymmetric. So I showed that this term was supersymmetric. So S is equal to S, let's call it free, plus S interaction, where this is S interaction. So the second exercise show that Q of S interaction equals 0, so that the whole action is supersymmetric. Okay? So that obviously you need to use both of these terms, otherwise it's not going to be supersymmetric. Okay, any questions? Sorry for going over time.
I think we
Yeah,
can enter the discussion sessions.
Yeah, go ahead. No, never too late. So, sorry, so this MMN is the angular momentum, the conserved angular momentum charge. So people usually use the letter M for, this M is the mass. Any other M's that I forgot? This is the mass. So this is supposed to be just mass times acceleration in the direction P. Other questions? Yes? So you could have asked, what does the electron field represent? Electron field is also a fermion, but you're never going to see an electron field. It's a fermion you're never going to measure in an experiment, but an electron, nobody would deny an electron has a physical meaning, right? So psi, x is the position, and psi is some extra variable, which is fermionic, and the spin is related to psi, but it's not something you're going to see in an experiment, psi. So if you like, it's just a variable which allows you to derive these equations, but you can also give it a physical meaning. It's just something that you can't see in an experiment. Other questions? Sorry, so I did this too fast, so thanks for the question. So I just wrote this equation here. So this was the equation for the ordinary relativistic particle, where A acceleration you think of as a 3 vector. So I just wrote it in terms of the component. So because I wanted to put these indices here, this P and P. So that's the only reason why, so P goes from 1 to 3. And I just means A is equal to A1, A2, A3. Is that clear? Yes. Sorry.
In the beginning of the lecture, you said that it was going to be SUSY in one dimension.
Yep.
Input one.
Yep.
But you have there basically X,
Yeah,
Y.
yeah. Okay, so this is confusing, and I'm not claiming it's not confusing, but there are two types of dimensions. And when I do quantum mechanics, there's the dimension of the world line, which is one-dimensional. But of course, the world line is embedded in space-time, which has another type of dimension, which in this case, I said 4 dimensions, so 3 space and 1 time. So there are two types of dimensions. There's the dimension of the world line, which is this 1, and there's the dimension of the space-time, which let me call capital D, is equal 4. So when you do quantum mechanics, you normally don't think of this as a dimension. You think of time as being just, well, I don't think I'm going to be able to avoid the confusion, but there are two different types of dimensions. The one here is the one of this P. So P is dd tau. Okay? So tomorrow, I should tell you what we're going to do tomorrow. Tomorrow we'll do a different case in which this P is 4. So that will describe supersymmetric field theory, in which, so some people use this language, it's called it first quantized, or quantum mechanics, where the variables which you quantize are the position variables. When you do field theory, you no longer quantize the position variables, you quantize the fields. It's called quantum field theory. So quantum mechanics is sometimes called first quantized, and quantum field theory is sometimes called second quantized. And the confusion is that here I'm using first quantized language. I'm quantizing the position variables. Tomorrow I'm going to discuss second quantized, which is like what Ricardo is discussing, field theory. So in fact, tomorrow you'll learn about spinors. So it turns out that you had lots of questions about spinors today, and tomorrow you'll see in gruesome detail how to do spinors in 4 dimensions. So it's not so complicated. It's very nice, but obviously you have to understand spinors if you want to understand supersymmetry in 4 dimensions. So you'll see that tomorrow. Yeah. The left side. This here? Sorry, why is this equal to this? Is that the question? Why is this? This is supposed to be equal to this. That's why I circled it in yellow. I just ran out of space, that's why. Yeah, that's my style. So it's to make you think more. Otherwise, you know. Go ahead. Yeah, go ahead. Why is this not 0? Well, remember, I erased it. So there's an anti-commutation relation, which is, so classically it's 0. But remember, I told you that psi m with psi n is equal to h bar a to mn. So that means, if suppose m and n are equal to 1, that means psi 1 plus psi 1 is equal to h bar, which means that psi 1 squared is equal to h bar over 2. So classically it's 0 because h bar equals 0, but quantum mechanically it's not. So spin is really quantum. You shouldn't think of spin as a classical spin, yes?
Just more on top of this question. Generally, the angular momentum tensor has a 0 in the main diagonal.
Yes, it's antisymmetric when m and n are the same, yes?
Yes, but you now those.
This is not psi, this is not MMN, this is psi. Remember, MMN is more complicated. It was,
Yes, that's there.
yeah, psi m, psi n minus. There was a question in the back somewhere. Okay, so as you said, there'll be an exercise session this afternoon. I'm around if, I mean, you can find me in my office, which is just nearby, so I'm happy to answer questions. So tomorrow, as I said, we're going to switch topics and we're going to do spinners.